Here is something that should bother you. The Sun, our nearest star, burns at about 15 million degrees Celsius at its core. Even at its surface, the photosphere, it is a roaring 5500 degrees Celsius. Earth sits just 150 million kilometers away. In cosmic terms, practically next door. So here's the question. Why is the space between the Sun and Earth freezing cold? Not a little cold, not cool, freezing, about minus 270 degrees Celsius. Just 3 degrees above absolute zero, the coldest temperature the universe allows. The most powerful heat source in our solar system is right there, blazing away. And the space surrounding it in every direction is almost as cold as it is physically possible to be. If you put your hand near a campfire, you feel the heat immediately. If the sun is billions of times more powerful than any campfire, why is the space around it not warm? Something is fundamentally different about how heat behaves in space. And that difference, once you understand it, will permanently change how you think about temperature, heat, and energy. Feynman would have loved this question, because the answer is hiding in plain sight, in a distinction most people have never been taught to make. Let us find it. G'day and welcome back to Curious Physics AU, the channel where we find the physics hiding inside the questions you never thought to ask. I am Abdullah, and today we are tackling one of the most counterintuitive questions in all of thermodynamics. Why is space cold when the sun is hot? To answer it properly, we need to understand three things: what heat actually is, how heat travels, and crucially, how it does not travel, and what temperature actually means at the quantum level. Because here is the thing, the way most Australians think about heat and cold, the way your school probably taught it, is missing a crucial distinction. A distinction that makes the difference between understanding a campfire and understanding the cosmos. Feynman always said, the difference between knowing the name of something and knowing something is everything. Today, we go from knowing the name to knowing the thing. Let us go. Before we can answer why space is cold, we need to establish something your school curriculum often blurs. Heat and temperature are not the same thing. This is not a pedantic distinction. It is the key to understanding almost everything in thermodynamics. Temperature is a measure of the average kinetic energy of the particles in a substance, how fast the atoms and molecules are jiggling. Higher temperature, faster jiggling. Lower temperature, slower jiggling. At absolute zero, theoretically no jiggling at all. Heat is the transfer of thermal energy from one object to another. It is a process, not a property. You cannot say an object contains heat. You can say thermal energy flows from a hotter object to a cooler one, and that flow is what we call heat. Think about a hot summer's day in Broken Hill, outback New South Wales. 45 degrees in the shade, the air temperature is extreme. You step inside a tin shed, and it feels like an oven. The metal walls of the shed are radiating thermal energy onto you from all directions. Now imagine you are standing in the same location, same sun, but in an open field with no shed. The air temperature is identical, but your experience of heat is completely different. Why? Because the mechanism of heat transfer, how thermal energy reaches you, is different. In the shed, thermal energy reaches you by radiation from the metal walls and by conduction and convection from the hot air touching your skin. In the open field, thermal energy reaches you only by radiation from the sun, which is intense in the direction of the sun but absent in other directions, and by convection from the hot air. This brings us to the three and only three mechanisms by which thermal energy can transfer from one place to another. Conduction, thermal energy transferred through direct contact between particles. Touch a hot Barbie plate, conduction burns your hand instantly. Convection, thermal energy transferred by the bulk movement of a fluid, liquid or gas, the hot air rising from that Barbie, the ocean currents redistributing heat around Australia's coastline. Radiation, thermal energy transferred by electromagnetic waves, photons, and which require no medium, no particles needed. Radiation travels through a perfect vacuum at the speed of light. Now, space is a near-perfect vacuum, almost entirely empty of matter. No matter, no conduction. No matter, no convection. In space, the only mechanism of heat transfer is radiation. And that single fact, radiation only, is the key to the entire mystery. Every object with a temperature above absolute zero emits electromagnetic radiation. This is called thermal radiation, or blackbody radiation, and it is one of the most fundamental phenomena in all of physics. The hotter an object, the more radiation it emits, and the shorter the wavelength of that radiation. The sun, at 5,500 degrees Celsius at its surface, emits radiation predominantly in the visible light range. That is why sunlight looks the way it does. The sun is so hot, it glows in visible light. A campfire, cooler than the sun, emits radiation predominantly in the infrared range. You feel it as warmth on your skin, even without touching the fire or being in the rising hot air above it. Your own body, at 37 degrees Celsius, emits infrared radiation continuously. This is how thermal imaging cameras see you in the dark. You are glowing, just at a wavelength your eyes cannot detect. Now, here is the crucial physics of radiation in space. When the sun emits radiation, that radiation travels outward in all directions at the speed of light, through the vacuum of space, carrying energy. But here is what that radiation is not doing. It is not warming the space it travels through. Radiation does not heat a vacuum. It cannot. There are no particles in the vacuum to transfer energy to. The photons travel through space carrying energy, but they only transfer that energy when they are absorbed by something. Think of it like this. Imagine you are at the MCG, Melbourne Cricket Ground, watching a game under the floodlights. The lights are blazing, enormously powerful, but the air between the lights and your eyes is not glowing hot. The light travels through the air without heating it significantly. Now, the space between the sun and Earth is 1 trillion times more empty than that air at the MCG. The radiation from the sun travels through it, carrying energy, but transferring essentially none of it to the vacuum itself. The vacuum stays cold, not because the sun is not radiating, but because there is nothing in that vacuum to absorb the radiation and become warm. Space is not cold because the sun is far away. Space is cold because space has no matter to absorb the sun's radiation. Temperature requires particles. Vacuum has none. That is the real answer to the question. Now, here is where it gets genuinely interesting and where we need to be precise about what temperature even means in a vacuum. Temperature, as we defined it, is the average kinetic energy of particles. Fast-moving particles, high temperature. Slow-moving particles, low temperature. But what is the temperature of a vacuum, a region with no particles at all? Strictly speaking, a perfect vacuum has no temperature. Temperature is undefined in the absence of matter. When scientists say space has a temperature of minus 270 degrees Celsius, what they actually mean is this. If you placed a small object in deep space, far from any star, and let it reach thermal equilibrium, it would settle at about minus 270 degrees Celsius. That temperature is set by the cosmic microwave background, the afterglow of the Big Bang we discussed in our previous video. Even in the deepest, emptiest regions of space, there is a faint bath of microwave radiation left over from the early universe. That radiation has a temperature, about 2.7 Kelvin above absolute zero, and any object in deep space will eventually radiate away heat until it reaches equilibrium with that background radiation. Minus 270 degrees Celsius is not the temperature of the vacuum itself. It is the equilibrium temperature of matter placed in that vacuum. So why do astronauts need temperature-controlled suits? Not primarily because space is cold, but because of the two competing processes happening simultaneously. On the side of the astronaut facing the sun, solar radiation is being absorbed by the suit. Without active cooling, the suit would heat up rapidly, potentially to over 120 degrees Celsius in direct sunlight. On the side facing away from the sun, the suit is radiating thermal energy into the cold of deep space, losing heat continuously. The challenge for spacecraft and spacesuit engineers is not keeping warm in a cold environment. It is managing the extreme temperature difference between the sunlit and shadowed sides and maintaining a stable temperature in between. Australian-born engineers at NASA and the Australian Space Agency work on exactly these thermal management challenges. The physics of radiation in space is not just academic. It is engineering reality. Now, let us go one level deeper. Because the physics of thermal radiation, the phenomenon that explains why space is cold, is also the phenomenon that triggered the quantum revolution. In the late 1800s, physicists tried to use classical physics to predict how much radiation an object emits at each wavelength. Their prediction, derived rigorously from classical electromagnetic theory, was catastrophic. Classical physics predicted that objects should emit infinite energy at short wavelengths, in the ultraviolet range and beyond, an infinitely bright, infinitely energetic glow from every warm object. Clearly, that does not happen. Your kettle does not destroy the universe when it boils. This disaster was called the ultraviolet catastrophe, and it signaled that something was fundamentally wrong with classical physics at the atomic scale. In 1900, German physicist Max Planck found a mathematical formula that matched the observed blackbody radiation spectrum perfectly. But to make it work, he had to make a radical assumption. Energy is not continuous. It comes in discrete packets, quanta. The energy of each quantum is proportional to the frequency of the radiation, E equals h times f. Energy equals Planck's constant times frequency. This was the birth of quantum mechanics, triggered by the question of why hot objects glow the way they do. The same physics that explains why space is cold launched the greatest revolution in the history of science. Feynman, who spent his career developing quantum electrodynamics, always traced the quantum revolution back to this moment. Planck's desperate mathematical trick, quantizing energy, turned out to be the deepest truth about the universe. The radiation from the sun, the coldness of space, the glow of your campfire, the infrared signal from your body, all of it, described by quantum mechanics, all of it, governed by Planck's constant. A constant so fundamental, it appears in virtually every equation in modern physics. The answer to why space is cold turns out to be connected to why quantum mechanics exists at all. That is the kind of connection Feynman lived for. Now, here is a twist that will genuinely surprise you. We have been asking why space is cold when the sun is hot. But here is the reverse question, and it is equally puzzling. The surface of the sun, the photosphere, is about 5,500 degrees Celsius, hot enough to melt anything we know. But the sun's outer atmosphere, the corona, the wispy halo of plasma you see during a solar eclipse, is about 1 to 3 million degrees Celsius. The atmosphere of the sun is hundreds of times hotter than its surface. That is like standing 1 meter from a campfire and finding that the air 10 meters away is hundreds of times hotter than the fire itself. It violates every intuition about how heat works. It seems to violate the second law of thermodynamics. And it has puzzled solar physicists for decades. Australian solar physicists at institutions including the University of Sydney and Monash University have contributed to research into the coronal heating problem. NASA's Parker Solar Probe, launched in 2018, is currently flying closer to the sun than any spacecraft in history to investigate this exact mystery. The leading theories involve magnetic reconnection, explosive releases of magnetic energy in the corona, and Alfvén waves, magnetohydrodynamic waves carrying energy from the solar surface into the corona. But the coronal heating problem is not fully solved. It remains one of the most active research areas in solar physics. So we have two mysteries that seem to contradict each other. Space near the sun is freezing cold because radiation does not heat a vacuum. But the sun's own corona is millions of degrees hotter than its surface for reasons we still do not completely understand. The universe is not simple, and solar physics is very much alive. Now, let us bring this back to Earth, literally, because the physics of radiation in space has profound consequences for life on our planet. Earth sits in the sun's radiation field. Solar radiation, predominantly visible light and near-infrared, strikes Earth's surface and is absorbed. The surface warms, and then, as every warm object does, Earth radiates thermal energy back outward. But here is the crucial difference between Earth and the Moon. The Moon has no atmosphere. Solar radiation reaches the lunar surface directly. The sunlit side reaches about 127 degrees Celsius. The shadowed side plunges to minus 173 degrees Celsius. Extreme, rapid, unmoderated. Earth has an atmosphere, and that atmosphere changes everything. Incoming solar radiation, mostly visible light, passes through the atmosphere relatively freely. It warms the surface. The surface radiates thermal energy back, but now as infrared radiation, longer wavelength, lower energy, and certain gases in the atmosphere, water vapor, carbon dioxide, methane, absorb this outgoing infrared radiation and re-radiate it in all directions, including back toward the surface. This is the greenhouse effect. Not a conspiracy, not a simplification. Straightforward radiation physics. Without any greenhouse effect, Earth's average surface temperature would be about minus 18 degrees Celsius, entirely frozen, no liquid water, no life as we know it. The natural greenhouse effect raises Earth's average temperature to about 15 degrees Celsius. The difference between a frozen rock and a living planet is the radiation physics of greenhouse gases. Australia experiences some of the most intense solar radiation on Earth. Our vast continent, much of it arid and cloud-free, absorbs enormous amounts of solar energy. The Great Barrier Reef, the Red Centre, the Southern Ocean, all shaped, fundamentally, by the physics of how radiation interacts with Earth's surface and atmosphere. Understanding radiation physics is not just academic for Australians, it is the physics of our home. We have mentioned absolute zero several times. Let us spend a moment on what it actually is and why it matters. Absolute zero is 0 Kelvin, minus 15 degrees Celsius, the temperature at which particles have minimum possible thermal energy. Now, can you actually reach absolute zero? The third law of thermodynamics says, no, you can approach absolute zero asymptotically, getting closer and closer, but never actually reaching it. Each step closer requires exponentially more effort. The last fraction of a degree is infinitely difficult. The coldest temperature ever achieved in a laboratory by Australian physicists at the Australian National University in Canberra, among others, is about 38 picokelvin. That is 38 trillionths of a degree above absolute zero. Colder than anywhere in the natural universe. Achieved in a laboratory in the Australian Capital Territory, at temperatures approaching absolute zero. Matter behaves in extraordinarily strange ways. Quantum effects that are normally hidden become dominant. Bose-Einstein condensates, where atoms lose individual identity and behave as a single quantum entity. Superfluids that flow without any friction. Superconductors that conduct electricity with zero resistance. These quantum states of matter, only accessible near absolute zero, are active areas of research at Australian universities including ANU, UNSW and the University of Queensland. The coldness of space and the quest to reach absolute zero in the laboratory connect to some of the most exciting frontier physics being done in Australia today. Let me close with the lesson Feynman would draw from today's question. The question, why is space cold when the sun is hot, sounds simple. It is the kind of question a child asks, and for that reason, adults often dismiss it, or give a hand-wavy answer, or change the subject. Feynman never did that. He believed that questions asked by children, and questions that seem simple on the surface, are often the most profound, because they cut to the heart of things that adults have stopped questioning. Why is space cold when the sun is hot? Because heat transfer requires a medium for conduction and convection, and space has none, because radiation travels through vacuum without heating it, only transferring energy when absorbed by matter. Because temperature is a property of particles, and vacuum has no particles. Each of those statements is precise. Each connects to a deep principle. Each took centuries of human thought to establish, and the same physics, Blackbody radiation, that answers this simple question, is the physics that launched quantum mechanics, that governs Earth's climate. That shapes the habitability of our planet. That drives the research programs of Australian physicists at the frontier of knowledge. Simple questions, deep answers. That is physics. That is Feynman. That is curious physics AU. So let us bring it all together. Feynman style. Space is cold, not despite the sun being hot, but because of how heat actually travels. Heat can only move through space by radiation. Electromagnetic waves that travel through vacuum without warming it. Radiation only transfers energy when it is absorbed by matter. Space has almost no matter. So the radiation passes through, carrying energy, but leaving the vacuum cold. Temperature is a property of particles. Vacuum has no particles. So technically, deep space has no temperature. The minus 270 degrees Celsius figure is the equilibrium temperature of matter placed in that vacuum, set by the cosmic microwave background. Astronauts need thermal management not because space is cold, but because the sunlit side overheats while the shadowed side radiates heat away constantly. Blackbody radiation, the physics behind all of this, triggered the quantum revolution when Max Planck discovered energy is quantized. Earth's atmosphere, through the greenhouse effect, uses this same radiation physics to maintain temperatures that make life possible. And the sun's corona mysteriously millions of degrees hotter than its surface, remains one of the great unsolved problems in solar physics. If this video changed how you think about heat, cold, and the physics of space, smash that subscribe button and join the Curious Physics AU family. New videos every week built for Australian students and anyone who refuses to accept a hand-wavy answer. Drop a comment below. What surprised you most? Space having no temperature? The ultraviolet catastrophe launching quantum mechanics? The sun's corona being hotter than its surface? Tell me what got you. Share this with someone who asks great questions and deserves a great answer. For the HSC and VCE students, this video connects directly to your thermodynamics, wave, and modern physics units. The radiation physics here is examinable, and now you understand it at a level that goes well beyond the syllabus. I will catch you in the next one.